So now we've talked about the electrostatics when we have charges just floating around in space. One up here and one here, maybe a rod down here, maybe a plane over there. But now we want to think about something more realistic. We want to think about charges in materials and how materials behave in terms of electrostatics. So there are many, many materials in the world that do many, many amazing things. But for the electrostatics in freshman physics, we can basically narrow it down to just two kinds of materials. So let's look at charge in materials. So we can narrow it down simply to insulators and conductors. So what goes on in an insulator? Basically, all you need to know is that the electrons are bound to their atom. They're not free. So if we think about the inside of an insulator, we could imagine that the atoms, the nuclei of the atoms, are arranged in some way, maybe like this. And the electrons are stuck with their atom. So they're going around in a cloud like that, and they can't leave. And I've drawn way too many of them. Now it is true they can interact. So a chemical bond is these two electrons talking to each other. So there can be forces between them, and they can create bonds, but they can't really go anywhere. All right? They get a little bit electrostatically interesting because their surface is sticky. Like in the Teflon rod, we know the electrons can't go anywhere, but if we rub the surface, we can put extra electrons on the surface and we can give it a surface charge. That's how we can see electrostatic phenomenon. Or we could rub it a different way and remove charge from the surface and lower the charge and make this side essentially positive. So you can play a little bit with insulators, but basically the charges don't move. The other kind of material is the conductors. Now, you can make conductors a few different ways. So the ones I'm going to talk about are metallic conductors. Okay. The example I'm going to give, the definition I'm going to give applies to metals. And throughout the class, I'll say metals a lot. And when I just say metal, I really just mean metallic conductor. Okay. So in a metallic conductor, the electrons move freely throughout the material. Okay, so if I were to draw a metal like this, here's your atoms, like that, and I left out one word, some electrons move freely through the material. So some of the electrons are still bound, just like they were in the insulator. These electrons do not leave their nucleus, but then some are just free to wander around. They can go visit this atom for a while, see how it's going, and then go see this atom, and send a message over to this atom about this atom's parents. So they can go all through the material and flow around. Okay? Because the charges are free to move, that allows a lot of different things to happen, as you can imagine. So you can actually think of this motion, you can actually kind of treat it as a gas. You can actually get pretty far in physics in figuring out the properties of a metal just by treating it as a gas of electrons. But eventually you run into trouble because there's this thing called quantum mechanics that ultimately makes it not behave like a simple gas. Okay, so then moving forward, now that we have these two materials, we're going to come up with new ways to charge things up, other than rubbing cats and stuff like that. Okay. Well, we do have a question before we keep going. Let's see. So let's see. JVJ24601. So are all conductors charged? Let's see. Okay. Yeah. No. Okay. Yeah, so the question is, are all conductors charged, right? So I have described these kind of different. Here you've got the regular situation. Here's an atom. The atom is neutral. It's got protons here, electrons here, the same number. It's also true here. The protons are positive, the electrons are negative, but some of the electrons are stuck, but they're not enough to counteract the charge of the proton. So you need these free electrons to make the thing neutral. So the answer is no, the metallic conductor is not charged. It's still neutral. It's just some of the electrons that make it neutral are free to move around. So we still have the same number of protons and electrons. There's not any extra electrons. It's just the way the chemical bonding works out, some of them are free to move around. This also is relevant because it's neutral. What this is also explains why the electrons don't leave the material. So if one of the electrons said, I'm going to come out here and spin around, that would actually leave the thing positive. It was neutral, we took away an electron, now it's positive. So if this thing is positive and this is a little electron, it's going to be sucked right back in. So the material, the positive nuclei of the material act sort of like a box or an energy well for the electrons. And they can move around, but they have to stay in the material.